at the end of the previous video, I was thinking about the spectrum of activity and some thoughts that might go into choosing antibiotics, and there's a lot to it. So the way we actually do choose antibiotics is we try to figure out what is causing the infection, and we try to match the antibiotic to the drug. And you can tell this is not a slide I originally made. This is one that somebody gave me because of the word bug, and it really doesn't matter. You'll hear people say bug. Yeah, that's how it works. Doesn't matter. But yeah, we try to match the microorganism with some kind of drug that can treat it. And so here's how you can kind of make educated guesses about what is causing the infection before you get lab results back that tell you what was causing the infection. And so, like, when and how did the patient become sick? What part of the body did it show up in? Those give you guesses. Those narrow it down usually. And then you have to think about where else has the infection gone to. And some other things you'd have to think about when you're first learning about antibiotics. You really have to think about balancing the power of an antibiotic drug against its toxicity in a human. So we have some great antibiotics that are carcinogens. So we don't use them unless there's an extreme life-threatening infection. We also have some antibiotics that are very inexpensive. Like the one I was just thinking about, it's very toxic, it's very cheap, so it's used all over the world except in the US. Some of the great antibiotics we have are extremely expensive, so you wouldn't use them unless you had to. And how convenient are they? Can you give a pill to an outpatient, send them home with a bottle of pills that they take? Penicillin V is a version that a person can take as a pill. But the question is, will it be absorbed into their bloodstream? Where in the body will it go? Will it go into the brain if they have meningitis or encephalitis? Probably not. If you need to treat an infection in the gut, you don't want an oral antibiotic that is absorbed out of the gut into the bloodstream. So, do you have to do an intravenous introduction of the antibiotic? In that case, you can't send the person home. And lots of other things like that. If you're giving someone treatment for tuberculosis, you have to give them a multi-antibiotic cocktail that they have to follow for several months. Anything you can do to make that more convenient for the patient makes them more likely to follow your instructions. And that makes them more likely to have successful treatment. So there's a lot of that stuff around choosing the antibiotics. In pharmacology, I mentioned briefly, the antibiotics have to get to the infection, and they have to achieve a high enough concentration at the body site where the infection is happening for a long enough time to kill enough of the cells that our immune system can mop up the rest. And so that can be tricky. Some examples, like I mentioned, meningitis and encephalitis, those are really hard and sometimes impossible to treat because most antibiotics will not cross the blood-brain barrier. So if you happen to work in an emergency room and you know you'll see some cases of bacterial meningitis, you have to know which antibiotics will cross the blood-brain barrier. In other cases, things happen like in bacterial endocarditis when heart valves have infections. Some of the bacteria that will infect heart valves make massive, thick biofilms, and antibiotics just won't diffuse into that very well, so antibiotic treatment won't be very effective. You have to use an extremely high concentration of antibiotics to treat endocarditis. And you might have to ultimately send the person in for surgery. So that's terrible. So that's the pharmacology. It's just another thing to think about when choosing an antibiotic is will it get to the right site of infection? I also mentioned trying to achieve high concentrations of antibiotics in the gut. Well, some antibiotics are excreted into the gut, right? They're treated by the liver and excreted into the gut. And so some of those you can inject and they will go into the gut. So there's a lot of this pharmacology you'd have to know. And in a lot of cases, a person wouldn't learn every antibiotic. They'd learn every infectious disease and learn the major antibiotics that treat it. And that would be the context for learning their pharmacology. If you ever do go off and learn how to prescribe every antibiotic, shoot me an email and tell me everything you know, because I'm curious about it. So, why do antibiotics fail? Why would somebody ever have a reason to say, I took the antibiotics, but then I became resistant? I mean, what they mean, of course, is the bacteria became resistant. But why would that ever happen? Well, if there's a mutant in this population of bacteria that's causing their infectious disease, if these mutants are there and they treat with an antibiotic, they never had a chance because there are enough mutants that the antibiotic will kill off their competition and the mutants will take their place. And then you'll have to use a different antibiotic. Why doesn't this always happen? Why do antibiotics ever work when there is genetic diversity among microorganisms? Well, one good reason is that we have immune systems. Antibiotics don't have to kill every cell. They have to kill enough cells that our immune system can take over. And so if you have macrophages and neutrophils hunting down these bacteria, if they're outnumbered and overwhelmed, well, macrophages and neutrophils aren't enough. But if you have small numbers of remaining bacteria, macrophages, neutrophils, other phagocytes in the spleen and liver, they're ultimately going to be able to take care of it. So if this happens, it's very bad luck, and it shouldn't happen. It would be better if it never did. What happens if your patient stops taking the antibiotics before they've taken all of them? Why is that a bad thing? Well, the idea here is that some bacteria, some mutants, may be partially resistant. Maybe they need 5 mutations to become resistant, and they have 3 of them. And that gives them some resistance. If you take antibiotics long enough, they will get all through the body and they'll accumulate in the sites of infections at high enough concentrations for high enough durations to kill even those. That's what we want. To kill even the susceptible ones, so the sensitive cells, and the partly resistant cells. If you take antibiotics for the right amount of time, you'd kill all of them and the immune system would finish the job. But if a person stops, and there are some of those mutants left, these mutants will keep growing, making new cells, and accumulating more mutations, and they could become a resistant population. And at that point, they'll come back, and the original antibiotic won't work anymore. That's really what we want to avoid. If you send somebody home with antibiotics, you want that to be the end of it. But if they stop too soon, that really increases the chance that they're going to have to come back and start over with a new antibiotic. And I always want to bring you back to these graphs of the exponential decay and decimal reduction times. Because this is what I want you to have in your head whenever you're thinking about reducing a bacterial population or any microbial population, whether it's on a countertop or in a sink or in your forearm, wherever. It takes time to kill microorganisms, and they die in an exponential process. So if we're looking at this graph, let's say these were cells in your patient's forearm. Well, the antibiotics might drop in an hour, maybe. I may ignore these numbers, but in a certain amount of time, population could go from 1 million down to 100,000, and the immune response would keep going. But once the antibiotics got down to this level, maybe the immune response would stop because there just wouldn't be that many live cells anymore, and the patient would feel better. But there's still this many cells in the patient, and they could grow and get back up to this level if you stop the treatment. So that's why we want to keep people treated until we're certain that the treatment has worked. So I will stop showing you these graphs now, and we'll move on to other things in the next video. So I'll see you there.